Hello, this is Jack Jackson. Let's look at another finite geometry. This geometry is going to have 5 points. Before we get started, let's consider the following set of postulates. Postulate 1, each pair of distinct points determines a line. Postulate 2, each set of 3 distinct nonlinear points determines a plane. Postulate 3, if 2 points lie in a plane, then any line containing them also lies in the plane. Postulate 4, if 2 distinct planes intersect, then their intersection is a line. At postulate 5, the geometry contains at least 4 noncoplanar points, or 5a. 5b, the geometry contains at least 3 noncollinear points, and 5c, each plane is a set of points of which at least 3 are noncollinear. Now, if you think about Euclidean geometry, you'll see that it's a model for this set of postulates. All these statements are either postulates or propositions in Euclidean geometry. Now we're going to examine a new finite geometry. For this geometry, we're going to create a physical illustration and check which of the postulates above are true and which are false. Now, checking is actually fairly easy to do visually by inspecting the illustration, but actually documenting these checks takes some attention to detail. We'll call this type of proof a proof by exhaustion, not because we exhausted, although we may be, but because we have exhausted all of the finite many things that we can check. We'll make use of some tables to help record checks and make sure we didn't miss anything. And these are going to form a large part of a formal proof. So here's our geometry. The points are A, B, C, D, and E. The lines are the set ABC, the set AD, the set AE, the set BD, the set BE, the set CD, the set CE, and the set D. And then we have planes. The one will be the set ABCD, one will be the set ABCE, another will be the set ADE, another one will be the set BDE, another one will be a set CDE. So all of the planes have either 4 or 3 points. All the lines, most of the lines have 2 points, and there's one line with 3 points in it. So here's what I'd like you to see if you can do before you move on. See if you can make an illustration for this model using Euclidean line segments to indicate incidents, points being on the same line. And this can be done actually in a 3D Euclidean space so that planes are parts of Euclidean planes. So see if you can figure out how to do this yourself. Try it. Press pause now. Well, here's a link right here to a GeoGebra construction that I have done. And this is the finite geometry right here. I've made the, let's see, 1, 2, 3, 4, 5 planes, which you see them labeled. A is the origin, B is the point. Let's see, this is the red is the x-axis, so this is point 1, 0, 0. C is the point 2, 0, 0. D is the point 0, 0, 1, and the point E is 0, 1, 0 on the y-axis there. D's up on the z-axis. And then they have some line segments here to indicate the lines. Notice the points A, B, C are all on the same line. AD is a line. AE, A and E is a line, and so forth. BE is a line. BD is a line. The planes then are basically the part of the XY plane, the A, B, C, and E. There's that one. A, B, C, and D is part of this, I guess it's the XZ plane, A, B, C, and E. Part of the, let's see, the YZ plane, AED, or AD and E, that's a plane. BDNE, that's a plane that kind of cuts across here. The pink one here is BDNE, and CDE, that's like the top face going along the side here. So the plane, there's a plane going along there on the top. So there's a plane, kind of slicing here and across there, and then the ones that are bounded by the coordinate planes there. Okay, now remember, just as in our other finite models, the planes are not all that I've got shaded. It's just those particular points there, and the lines are not There's no points on this line except for A, B, and C, for example. Nothing else. And it satisfies all of those postulates there. Okay? Well, does it satisfy all of them? That's what we want to check. Okay? So see if you can kind of just look at it, and then we're going to talk about how to actually document this. So each pair of distinct points determines a line. You got to show that no matter which 2 points you pick, there's only one line that contains them. There is one, and there's only one, right? That's what determine means, a line. Determines a line means. Each set of 3 distinct noncollinear points determines a plane. You got to show that no matter which 3 points you pick, as their laws are not all in a straight line, then there's exactly one plane that contains them. Postulate 3, if 2 points lie in a plane, then any line containing them also lies in that plane. So take 2 points, any 2 points, find a plane that it's in, and take any line that goes through those 2 points. It needs to be all the way contained in that plane too. And there are at least 4 noncoplanar points, C, D, and E, for example. 3 noncollinear points, D, E, and A. Each plane is a set of points which at least 3 are noncollinear. Okay, so we want to document all of that. So the documentation part is the hardest part. There's the thing that we were just looking at. So postulate 1 says each pair of distinct points determine a line. In other words, line. It says if x and y are distinct points, then there exists exactly one line containing both of them. So what we need to do is look at the pairs of points. Now we have 5 points, A, B, C, D, and E. If you do 5, choose 2, that's okay, that's 10. So there's 10 combinations, A with B, A with C, A with D, A with E. That's all the ones with A. You've got B with C, B, D, and B with E. Then you got C with D, C with E, and then you got D with E. So that's a systematic way to go through to make sure we got all 10. Okay, now let's look at what lines contain A and B. Now here are the lines down here. Well, the only line that contains A and B is the line ABC. There is one and only one. How about the ones that contain A and C? Well, A and C are contained in that line. None of the other lines contain both A and C at the same time. How about A and D? No there, no for all these, but yes on this one right here. So that one is. In fact, most of the rest of these sets of 2 points actually are a line. B and C is a little different because it takes all 3 points to make the line there. But notice that in every case we were able to fill in exactly one line in the second column, second row, and that works out. If we had a row, if we had just even one spot where we could put 2 different lines in that row, or none at all, then postulate 1 would be false. But it turns out that postulate 1 is true. Postulate 2 says each set of 3 distinct noncollinear points determines a plane. So now we got to get 3 points together. Now there is a set of 3 points that are collinear. That's A, B, and C. So we're going to eliminate that one. Let's see. 5 choose 3 is also 10. But we're going to eliminate this 1, so that should leave 9 here. 3, 4, 5, 6, 9. Yeah, there's all 9 there. Why did we eliminate this one? Because it says these have to be non-collinear points. Okay, so that doesn't say anything about that, collinear points. Now, how many planes are containing those points in the set? Okay, let's take a look. Well, here's our list of planes. Which ones have A, B, and D? Okay, no A, no A, no B, no D. Yeah, that one has A, B, and D. So that's it. That's our plane. Which ones have A, B, and E? No A, start to right, no A, no A, no B. That one does it. That one's no E. So this one is the only one. Okay, and you just go through here one at a time and just double check. Again, it's maybe easier to check by just looking at the picture, but to document it on a piece of paper it's a little little bit trickier. And so we have to make a table like this to check it. So let's try A, C, and D. This one contains A, C, and D. No D, no C, no A, no A. So that's the only one. And likewise, you go through every single one of these. I'll let you finish it on your own. Pause if you need to do this yourself. I encourage you to do it. And you'll see that in every single case, we can put one and exactly one and only one planes in that line to make it work of our table. So this next one, if 2 points lie in a plane, then any line containing them also lies in the plane. The best way to document this one I found was to put it 4 lines to the table. So we started with pairs of points. Again, there are 10 of those. We missed all the lines that contain them, which each case there's just one. And then we looked at the plane containing the pair. So these planes contain A and B. These are A and C, and so forth. And the question is that line in, well, in each case there were two planes. Is that line in both of those planes? And the answer was yes in every single case. And so we can say yes in every single case. Then we have that postulate is satisfied. It turns out that it was actually a little bit easier to check because since all the lines are actually just sets of 2 points, once the 2 points are in the plane, that whole line's in the plane. The only one we really needed to check was that one with 3 points in it. So here we just check the one with 3 points. We take any 2 points from A, B, and C and just check that. So really it's only those three columns of the table that we really need to check because those are pretty automatic. How about postulate 4? If 2 distinct planes intersect, their intersection is a line. So we take all of our planes here, 1, 2, 3, 4, 5. We take them 2 at a time. That's going to be 10 pairs, and here I've listed all the pairs. Then I've looked at their intersections. So if you look here, they've got A, B, and C in common. This one has A and D in common, and so forth. And then you look at all of these and see if these are in our list of lines. And the answer is yes for every one. So since we got a yes for every column, postulate 4 is true. The geometry has 5 points, so that's at least 4, but let's see, how about there are 5 sets of 4 points. These 4 are coplanar point sets, but the other 3 sets are non-coplanar. Any one of these would be enough to satisfy 5A. 3 non-collinear points. Well, there's only one set of 3 collinear points. So take any other set of 3 points, any of these, just one of these sets of 3 points would be a set of 3 non-collinear points. And that'd be enough to satisfy 5B. Each plane is a set of points of which at least 3 is non-collinear. So here are the planes, all 5 planes, and here are sets of points within there that are non-collinear. We had overkill on these 2. We only needed one of these 3 and one of these 3 to make it work. Having extra is fine, but we had to have at least one set of 3 points that were non-collinear. You could have a set of points. This one does. Notice these 2 right here have a set of 3 points, A, B, and C, which are collinear. That's okay. It doesn't matter. So all 3 parts of the postulate 5 are true. It satisfied all 5 postulates. So this is a model for this particular geometry. Not necessarily the only model. I think we said that Euclidean geometry works for this one as well. So that gives you an example of what it means to check all of these for a finite one. Again, I think you probably could have just checked those things visually by looking at this model once you're satisfied that this model accurately sort of illustrates what's going on here with the planes, extra C there, and lines, points, lines, and planes. But to actually document that and make sure that we didn't miss anything, that's what required a lot of these tables.